Okay, so in this video, we're going to start the differentiability handout. And so the first part of the handout is just some explanation stuff. One of the things is this limit definition for slope at a specific point. So there's one, here's one right here. And then you could also, so this is the one that looks like this. You pick a point, let's say here's your function, and we wanted the slope at this point right here. Then that point would be like a f of a. And then I'd pick another point nearby and call it a plus h, f of a plus h. And then this line would have the slope of f of a plus h minus f of a all over a plus h minus a, which always turns into h on the bottom. And then if I make h get really, really small, this turns into a tangent line at a instead of the secant, the blue line instead of that. And then the alternative definition is this one over here, which is the same exact thing, except instead of calling it a and a plus h, we call it a f of a and b f of b. And in this case, I make b turn into a. That's why the limit down here says b goes to a. And now we have a new term for this entire thing. It's called the derivative of f at x equals a. And so the new notations, it all means the same thing. It still means slope of f at a specific point a. And there's this new notation, f prime of a, that we can use, which means the slope of f at a. And then there's also this one right here, df dx, evaluated when x equals a. And the way that I think about this one is you're used to seeing delta y over delta x, which sometimes you see as delta f over delta x, the change in the f values over the change in x values. Well, the little d to me, so this is a change in y over a change in x. Because in each case here, you could draw a little slope triangle, and this would be your delta y, and this would be your delta x. Or you could do the same thing right here. This is delta y, this is delta x. But if I'm talking about a slope at a single point, one way that you could think about doing that is by taking a triangle that is so infinitely small that you have just a really tiny change in y and a really tiny change in x. And you're essentially finding the slope of a point that's super close to your original point, slope through those 2 points. So it'd be like a small change in y over small change in x. This triangle is capital D in Greek. And if it's a small change, well then let's just use a lowercase instead. And then this means when x is a. So those are all notations for the same thing. And in general now, we've been doing a lot of stuff where we say at x equals a, but now we're just going to leave it as x instead of x equals a. And you can come up with something called the derivative function. You also just call it the derivative of f. Okay, so in the last class, you differentiated, which means found the derivative of f of x equals x cubed by using the limit definition of derivative, which is this right here. This is always true. And then since f of x is x cubed, we plug in x plus h and we get x plus h cubed. Plug in x, we get x cubed. And then x plus h cubed, you can use the binomial theorem to expand it. And then you can evaluate all of these terms. And you get 1, 3, 3, and 1. And then you can simplify a little bit, and once you plug in h equals 0, you get 3x squared out of the whole thing. So if f of x equals x cubed, then we get that the derivative of f, the slope function of f, is 3x squared. So if f of x is x cubed, f prime of x is 3x squared. If f of x is x squared, we did this one last unit, and it turns out if you do the full limit as h goes to 0 of x plus h squared minus x squared all over h squared, then you're going to work this out and you'll end up with 2x, which is something that we actually did last unit, except with a's instead. Now, if you think about what happens if f of x equals just x. So f of x equals x. Well, that you already know the slope of it. It's in mx plus b form. So if so if I asked you what's the slope of x, well, the slope is 1. Right? So this one's going to be a 1 right here. All right, now let me show you a little bit here. This is 3x squared. Another way of writing 2x would be 2x to the first. This is the same thing as saying 1x to the 0. So you might be able to see a pattern here. If you have x cubed, you end up with 3x squared. Notice this number right here is the same as the number in front. And this power right here is the same as the number in front for its derivative. And this power right here is the same as its number in front for this derivative. Not only that, notice that these powers are always 1 less than the powers that show up over here. So if you had to guess, if I gave you the function x to the 4th and I said, what's the derivative of that? Well, you might guess, well, let's bring the power down in front, 4, and then say x, and then lower the power by 1. And that turns out to be correct. And if I said if f of x equals x to the 10th, well, let's bring the 10 down, the power down, and then lower it by 1. And that actually turns out to be correct too. And so this power rule can be defined this way. If you have x to the n as your function, then the derivative is always going to be n times x to the n minus 1. Okay? And this is a super useful rule. Now, we're not proving it right now. We're just kind of analyzing a pattern and coming up with a general case. And it'll turn out that we'll prove it for n equals a positive integer, but this actually works for any value of n that you want. Okay. So, important rule, and I will write it down in this example too as well. So use the power rule to find the derivative of root x. Okay, so I'm going to write right here, f of x equals root x. And then on the side here, I'm going to write the power rule again. Power rule says if f of x equals x to the n, then the derivative of f equals n times x to the n minus 1. Supremely useful rule. Saves you a lot of having to write out that limit notation stuff. Okay, well, let me rewrite root x as x to the 1/2. So now when I want the derivative of x, I could use that full limit definition of f of x plus h minus f of x all over h. Or I could use this nice little trick here because it's in the form x to the n. So if I use my power rule, then I bring that n down in front. So this guy comes down in front. So that's the 1/2 x. And then I raise it to the original power minus 1. So it's 1/2 minus 1. So this becomes 1/2 x to the negative 1/2. Now originally I wrote it in root form. So I'm going to rewrite this. Let me get rid of the negative exponents. So that's like throwing the x to the half in the bottom. And then that's like 1 over 2 root x. Now you can see how much quicker that is than using the limit definition. That's very quick. And eventually you'll get to the point where you just look at this and immediately jump to that step in your head for f prime of x. So use the result to find f prime of 4 and f prime of 0. Okay. F prime of 4 is going to be 1 over 2 root 4. So that's 1 over 2 times 2, so 1/4. So now I know that the slope of root x when x equals 4 is a 4th. So this says slope of f at x equals 4 is 1/4. So it's pretty quick. F prime of 0, let's look at that. That's going to be 1 over 2 root 0, which is 1 over 0. That's undefined. So that means that f prime 0 does not exist. So that means that the graph of f has no slope when x is 0. Okay, well let's look at the graph of f. The graph of f looks like this. Starts at 0, 0, and goes off like that. That's y equals root x. When x was 4, let's say x is 4 right here, that slope, this slope right here, equaled 1/4. But at 0, if I tried to draw a tangent line at 0, well, it's an endpoint. I can't draw one specific tangent line. If I could draw one, it would look an awful lot like a vertical tangent here. But I can't draw, I mean, really, I could draw a bunch of tangent lines there. So that's why I don't get one single slope there, and the derivative is undefined. When I say, let's look at the domain of f, right? Because it asks, what's the domain of f? Well, domain of root x would be, x has to be anything bigger than or equal to 0. So it'd be 0 to infinity, like that. If I said domain of f prime, notice that's not actually the same thing as f. Here's f prime. And the domain of that is, I've got a square root, so it's still x is greater than or equal to 0, but since it's in the denominator, I can't have the equals 0 part. It's only bigger than 0. So that would be this. So the idea here is, notice that the domain of f and the domain of f prime are not actually the same. The domain of f prime is always going to be the same as f's, or missing something from f. But it's never going to be bigger than f itself. Okay. So let's go on to the next part, number 3. So in example 3, we're supposed to compare the right-hand and left-hand derivatives to show that the function is not differentiable right here. Okay, so we're looking around 1, 1, around x equals 1, basically. Okay, so let's examine what happens at x equals 1. So on the left side of x equals 1, we have this. The function of x is root x. That's what this part says down here, right? Y equals root x. So on the left side of x equals 1, this is how we define it. F of x equals root x. So we just did in the previous part, if we found the derivative, the left-hand derivative, then we get f prime of x. And we just did this up here. F prime of x is going to be this thing right here, 1 over 2 root x. So the left-hand derivative at 1, if I plug in just a little bit less than 1, then I'm going to get 1 over 2 root just a little bit less than 1, which is really 1 over 2 times 1. So it's a half. Okay, let me shrink this down a little bit. Okay, so let's look on the right of x equals 1. So on the right side of x equals 1, I've got f of x equals this line, 2x minus 1. Well, that means that the right-hand derivative, the slope on the right side, well, that's an easy derivative. If I say, look at the line 2x minus 1, the slope is always 2. Okay, so then let's look at, well, then what's the derivative going to be on the right side of 1? Well, it's 2. Since it's always 2, it's 2. Okay, so now let's look here. What we just figured out was that this part right here says that the slope on the left side of 1, right there, or actually even closer, like right there, just on the left side of 1, the slope equals 1/2. And on the right side of 1, right here, the slope equaled 2. And if I wanted to say that there's a slope that exists right at the point 1, then the slope on the left side would have to equal the slope on the right side. It's very similar to the continuity definition. Well, this doesn't have that. So what I would write is, let's see here. Since the left hand and right hand derivatives at x equals 1 are not equal, f prime of 1 does not exist. Now f prime 1 from the left exists, f prime 1 from the right exists, but since they're not equal, f prime 1 in general doesn't exist. So you would say f, another way of saying that is f is not differentiable, meaning no derivative exists, at x equals 1. And if you look at the picture, you know, you can draw a tangent line here, you can draw a tangent line there. Can't draw a single tangent line here. There are a whole bunch of tangent lines you could draw through there that work. So it doesn't have a single derivative there. In fact, it's got, in a sense, it's got two different kinds of derivatives, one on the left, one on the right. Okay, and we'll do example 4 also. So example 4 says, show that the function f has both left and right-hand derivatives at 0, but no actual derivative there. Okay, now before I jump into this one, I'm going to draw a quick picture for it. So on the left side of the graph, it's x equals 0, and then a parabola going this way, x squared. So this graph on this side is y equals x squared, and it includes 0, 0. And then on the other side of the graph, y equals 2x is going to be a straight line like that, y equals 2x. Okay, and we want to show that, and notice they're connected, it actually is continuous at 0, 0. So let's say this, note, it's continuous at x equals 0. That'll come in handy for problems that come up later. So let's look at the left and right hand derivatives around 0. So at x equals 0, we're going to look at on the left side. So on the left side, f of x, or let's say on the left of x equals 0. So on the left side of x equals 0, we've got f of x equals x squared. And so then that means that the derivative of f on the left side is going to be 2x using the power rule, right? So the power rule says bring that power down in front and then lower it by 1. So it's 2x to the first, really. Okay, so then if I said, well, what's the derivative on the left side of 0? Well, that's going to be 2 times 0 to the left, which is really 2 times 0, which is 0. So that means that the left-hand derivative of f at x equals 0 is 0, which means the slope on the left side of x equals 0 is 0. Okay, and you can kind of see it right here. Right there, if I just look at the red side, the slope gets really close to 0 right there. It turns flat just for a moment. Okay, so let me shrink this down. Ooh. And now let's look at on the right side of x equals 0. So on the right side of x equals 0, we've got f of x equals 2x. And that means that the derivative of f, well, since it's 2x, well, the slope's 2, right? And since I'm looking on the right side of 0, let's plug in the right side of 0. Well, no matter what, since the slope's always 2 on the right side, it's 2 there too. Okay, so that means that the right-hand derivative of f at x equals 0 is 2. So the slope on the right side of x equals 0 is 2. Okay, and you can tell that. I mean, right here, this line, slope always equals 2. Right there, just next to 0, the slope is 0. Well, that means that the slope right at 0 is undefined, right? Because on the left side of 0, it's 0. On the right side of 0, it's 2. So it suddenly changes. So what we would say is, since the left-hand and right-hand derivatives of f at x equals 0 are not equal f prime 0 does not exist. So f is not differentiable at x equals 0. Okay, I hope that helps a little bit. The next couple pages I'll do in a separate video.